Fibonacci. Long time ago, we met the Fibonacci numbers.
So that's a sequence that goes, we'll start with 0, and then 1, and then each subsequent term is the sum of the previous two. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and then it keeps on going.
I'd like a formula for the Fibonacci numbers.
So in this case, a sub 0 is 0, a sub 1 is 1, a sub 2 is 1, a sub 3, 0, 1, 2, 3, that's 2, a sub 4 is 3, and a sub 5, that's 0, 1, 2, 3, 4, 5. A sub 5 is 5. And what we're looking for is a formula for the nth term in terms of n, right? I want to know that a sub n is equal to something, but I want the something to involve n's.
Now maybe you're thinking, don't we already have a formula?
You're right. I mean, there's this formula. A sub n is a sub n minus 1 plus a sub n minus 2. This is the formula that we use to define the Fibonacci sequence, right? Each term is the sum of the previous two. The trouble is that this isn't a very useful formula, right? To calculate the 1,000th term using this formula, I'd have to calculate the 999th term and the 998th term. I'm really looking for some kind of formula that just involves, the usual kinds of math functions that I'm used to, maybe powers, multiplying, adding, subtracting, dividing, that sort of thing, and the number n, right? I don't want a formula that depends on my calculating all the previous terms to calculate the next term.
Is that even possible? I mean, how am I going to go about finding such a formula?
Here's the trick. The trick is to assemble the Fibonacci sequence into a power series. What do I mean? I mean, we should think about this function f of x, and it'll be the sum, n goes from 0 to infinity, of a sub n x to the n. But here these a sub n's are the Fibonacci numbers. So a sub 0 is 0, so I'm not going to write that. But a sub 1, the first Fibonacci number is 1, so it's x. A sub 2, next Fibonacci number is also 1, so plus x squared. A sub 3, the third Fibonacci number is 2, so 2x cubed. Next Fibonacci number is 3, so 3x to the fourth. The next Fibonacci number is 5, so 5x to the fifth. And it'll keep on going.
Now I can set up an equation that f satisfies.
Well, here's how it goes. I'm going to multiply f of x by x. So x times f of x is what? Well, if I multiply this by x, the x gives me an x squared. The x squared gives me an x cubed. The 2x cubed gives me a 2x to the fourth. The 3x to the fourth gives me a 3x to the fifth. And it would keep on going. And then I'm going to multiply this by x squared. So what's x squared times f of x? Well, then x times x squared gives me an x cubed. X squared times x squared gives me an x to the fourth. 2x cubed times x squared gives me a 2x to the fifth, and I'm going to keep on going.
Now I'll do some subtraction.
So I've got f of x minus x times f of x minus x squared times f of x. And that's equal to, well, the x survives. X squared minus x squared, that cancels. 2x cubed minus x cubed, that cancels. 3x to the fourth minus 2x to the fourth minus x to the fourth, that cancels. 5x to the fifth minus 3x to the fifth minus 2x to the fifth, that cancels. Well, everything cancels. And that's not a coincidence, right? The defining feature of this sequence of numbers, the coefficients a sub n, the Fibonacci sequence. So each number is the sum of the previous two, right? 5 is 3 plus 2. The next number over here is what? It's 8. And 8 is 5 plus 3, right? Because each term in the Fibonacci sequence is the sum of the previous two, I've rigged it so that f of x minus x f of x minus x squared f of x is just equal to x.
Well, what does that even mean?
So just totally ignoring issues of convergence, really just thinking about this entirely formally, what I've got is that f of x minus x times f of x minus x squared times f of x is just x. where f is the function given by a power series whose coefficients are the Fibonacci numbers. Now I'll factor out an f of x. I've got f of x times 1 minus x squared is equal to x. And I'll divide both sides by this. So f of x is x over 1 minus x squared.
Okay, here's the plan. I'm going to find another power series for that rational function. And then I'm going to equate the two power series, the new power series that I found, and the old power series, the coefficients of which are just the Fibonacci numbers. It turns out that when those two power series are equal, their coefficients are equal. And that way, I'll get a formula for the Fibonacci numbers.
Now I'm going to rewrite this function in I think what initially will seem like a much more complicated way. First, I'm going to define this other number that's actually traditionally called phi. This is the golden ratio. Phi is 1 plus the square root of 5 over 2. Okay, so that's this number phi. And I'm going to use phi to rewrite this function f. So it turns out that after quite a lengthy calculation, you convince yourself that this is 1 over the square root of 5 divided by 1 minus x times phi plus negative 1 over the square root of 5 divided by 1 minus x times not phi, but 1 minus phi.
How is that better? It looks like I've just made a total mess of things.
Well, the trick now is that I can write these each as power series. Here we go. This is 1 over the square root of 5 times 1 over 1 minus x times phi plus negative 1 over the square root of 5 times 1 over 1 minus x times 1 minus phi. But I have a power series for 1 over 1 minus something, right? So this is 1 over the square root of 5 times the sum, n goes from 0 to infinity, of x times phi to the nth power plus negative 1 over the square root of 5 times the sum, n goes from 0 to infinity, of x times 1 minus phi to the nth power.
Now I'll write this as a single series.
Okay, so this is 1 over the square root of 5 times the sum, n goes from 0 to infinity. I'll write this as phi to the n times x to the n plus negative 1 over the square root of 5 times the sum, n goes from 0 to infinity, of 1 minus phi to the n times x to the n. And now I'm going to write this just as a single power series. I'm going to collect together the coefficients here in front of x to the n. So this is the sum, n goes from 0 to infinity, of 1 over the square root of 5 times phi to the n minus 1 over the square root of 5 times 1 minus phi to the n, all of this times x to the n.
I can simplify that a bit.
Yeah, I could write this as the sum, n goes from 0 to infinity, of phi to the n minus 1 minus phi to the n over the square root of 5 times x to the nth power.
And here's the punchline.
Well, admittedly, we haven't been concerned about convergence at all, but at least remember where this came from. I mean, we derived this through a series of perhaps unjustified operations, but we started with just this power series where these coefficients were the Fibonacci numbers. Now I've got a new power series. And the upshot, or what I'm hoping here, is that if these two power series are equal, then their coefficients must be equal. And that means that this is a formula for this. This is a formula for the nth Fibonacci number.
For real, that is a formula for the Fibonacci numbers.
Well, let's try it. I mean, here's the 100th Fibonacci number. It's this pretty big number. So the idea here is that instead of trying to calculate a sub 100 by hand, I'm just going to plug in n equals 100 and compute this coefficient.
Let's estimate that without using a calculator.
Well, instead of writing 1.6, that's about what phi is, let's write 16 tenths. And instead of writing 16 tenths, let's approximate phi by 16 tenths written this way, 2 to the 4th for 16, so 2 to the 4th over 10. But if I write it that way, then it makes it a little bit easier to do the estimation. Because 2 to the 4th over 10 to the 100th power, well, that's 2 to the 400th over 10 to the 100th. But now 2 to the 400th, I can write that as 2 to the 10th to the 40th. And that's a smart move because 2 to the 10th I happen to know is 1024, so 2 to the 10th is practically 10 to the 3rd. It's about 1,000. But 10 to the 3rd to the 40th, well, that's 10 to the 120th. So altogether, the 100th Fibonacci number is, about 10 to the 120th power divided by 10 to the 100th power, and altogether then, I can guess that the 100th Fibonacci number is about 10 to the 20th.
Is that even close to being accurate?
Well, the actual retail value, if you remember, here it is. Here's the 100th Fibonacci number. And although it's kind of a pain to count the digits, that 100th Fibonacci number is approximately 3.54 times 10 to the 20th.
Well, rock on, rock star. We've estimated the 100th Fibonacci number armed with nothing but our wits. Now, this technique of analyzing a sequence by building the associated power series, that technique has a name.
This sort of trick where I analyze a sequence of numbers, in this case the Fibonacci sequence, by building a power series and then playing around with it like this in a sometimes formal way. This is called generating functions.
One reason why this is a powerful technique is that it lets you carry a problem from one area of mathematics into a whole nother area of mathematics. We started with a very combinatorial feeling problem, a discrete problem, a problem about sequences. And by applying this method of generating functions, we transported that problem into the realm of calculus. And I think this shows that mathematics, at its deepest levels, is not a collection of disconnected subjects. Mathematics is a single unified whole, and all of these different areas of mathematics are connected together.